Hi everybody, my name is Rochelle, and today we're going to be talking about X-ray diffraction. I will first talk about what X-ray diffraction is and how it works. Becca will then explain how to read X-ray diffraction data, and Kayla will finish up our discussion by talking about the applications of X-ray diffraction. X-ray diffraction, also known as X-ray crystallography, is a technique that identifies atomic interplanar distances and crystal structures within a material. Knowing these properties is important in understanding the physical properties and functions of materials. X-ray diffraction experiments are carried out in a machine called an X-ray diffractometer. There are two types of X-ray diffraction, powder and single crystal. In these experiments, X-ray beams are directed towards the crystalline sample. The electrons in the sample scatter the X-ray beams in such a way that the distance between the scattered beams are equally spaced and mutually reinforced. The distance between the scattered beams is on the order of 1 angstrom or 10 to the negative 10 meters, around the same size as X-ray beams and the distance between atoms. We can now measure the diffraction by recording the angles at which the beams are diffracted in the sample. Now, Becca will discuss how the recorded data can be interpreted.
So this is what typical X-ray diffraction graphs look like. They are straight lines with peaks at different points along the x-axis. There are some differences in the graphs that help us understand the materials we're looking at. For example, in this case, the locations of the peaks are different between the two graphs. This means that these materials have different phase angles and are therefore different materials. Also, graphs can represent mixtures of materials. As seen here, there are 3 different graphs representing 3 different materials. When these materials are combined, their graphs combine as well. As you can see, the different peaks present in the individual graphs are also present in the mixture graph. Since specific peaks correspond to specific materials, X-ray diffraction graphs can be used to find which materials are present in a mixture. Now Kayla is going to discuss in more detail the applications of X-ray diffraction.
X-ray diffraction, both powder and single crystal, can be used for various things. Some applications for X-ray powder diffraction include the characterization of crystalline materials, identifying fine-grained minerals like clay, determining unit cell dimensions, and measuring sample purity. Applications for single crystal X-ray diffraction consist of new mineral identification, determination of unit cell length, bond lengths, bond angles, and site ordering, characterization of cation-anion coordination, and variations in crystal lattice. One specific application that relates to our class well is using powder diffraction to find the dimensions of a unit cell. To do this, we use Bragg's law, which is n times lambda equals 2 times d times sine theta, where n is the order of diffraction, lambda is the wavelength of the radiation used, d is the interplanar spacing, and theta is the angle between the incident ray and the relevant crystal planes. Although the derivation of Bragg's law is quite complicated, the general basis of it is that, when satisfied, X-ray beams scattered from planes in the crystal will travel distances differing by exactly 1 wavelength when n equals 1.